Okay, welcome back. Today we will continue with our section 12.7. Last time I already finished up the first part, which is cylindrical coordinate system. Now we continue on spherical coordinate system. Now last time we already saw what spherical coordinate system look like. It's basically consists of three parts. The first part is the rho. The first component of the coordinate is rho. The second component is theta. And the third component is phi. Okay, let me put subscript S here to show that that's for spherical coordinate system. Now, what is rho? Rho is the distance from origin to that coordinate. This is rho here. Okay, so if we have coordinate P in space, then rho is the distance, direct distance from origin to that coordinate. And then the second component, theta, is the angle from XZ plane to the projection of that point on the XY plane. So the theta here is the same notion with the theta we have in spherical, in cylindrical coordinate system, the same with the theta that we have in polar coordinate system. Okay, and then finally, what is phi? Phi is the angle from positive z-axis to the rho. Okay. Now, last time we have seen how we convert from a rectangular coordinate system to spherical coordinate system. Of course, we need to do some examples, right? But let's do backward for now. Suppose we have spherical coordinate system and we want to find the x and the y and the z. Okay, now take a look on this graph here. Notice that the x is basically, if we look back, x equals to r cosine theta, is it right? From polar. And the y is r sine theta. In polar, the c is basically z. Okay, now then, if we go back further, what is that in spherical? From spherical, notice that your r here, take a look. If I see this r from this triangle point of view, this right triangle point of view here, okay, if I see that r sideways, you will see that this is the r, this is a c, and this is the phi, right? In other words, r equals to rho sine phi, is it right? Which is what I will replace that r by. This is rho sine phi cosine theta, and therefore the y will be rho sine phi sine theta, and the z will be rho cosine phi. Okay. Now suppose we have polar instead. So suppose we start from polar coordinate system. So we have r theta z. How do we go to rho theta phi in cylindrical coordinate system? Now notice that from this picture again, that rho is the hypotenuse of z and r, right? Okay, so rho equals to square root of r squared plus c squared. The theta will be the same. Now, how about the phi? Now, the phi will be equivalent to, actually, no, we don't need to do, that's actually just cosine inverse of z over rho, provided that we do the rho first. Okay. Now let's do some examples from our textbook. Let's see. I pick these questions here. This set. Suppose I pick number 18. Number 18, we have 2 pi over 4 and pi over 3 in spherical coordinate system. What will this be in rectangular coordinate system? Now the x will be r cosine theta, which is rho sine phi cosine theta. Of course, when you do that in your quiz or in your test, you don't need to write this formula. Just go ahead, plug in numbers. In this case, the rho is 2, sine phi is pi over 3, and times cosine pi over 4. Okay, but I do expect you to memorize those special values though. Okay, this is 2 times radical 3 over 2, radical 2 over 2. That's radical 6 over 2. The y component will be r sine theta, which is rho sine theta sine, rho sine phi sine theta. That's 2 sine pi over 3 sine pi over 4. I think they will be the same, huh? That's radical 6 over 2. And the c component will be rho cosine phi, which is 2 cosine pi over 3. That is 1. So the rectangular coordinate system, rectangular coordinate will be radical 6 over 2 for x, radical 6 over 2 for y, and then 1 for the c. Let's see the next one, number 22. Number 22, we have negative 1, 1, square root of 6 in rectangular. What will that be in spherical? First, the rho. The rho will be basically the Pythagorean application to the x and y and z. I get square root of 8, which is 2 radical 2. Okay, and then the theta is equivalent to tangent inverse of y over x. That's negative pi over 4. But the thing is, I need to see which quadrant it is located. Yeah, after I acknowledge you, then do that, but don't sign your attendance until I acknowledge you. Okay, so x is negative 1, y is 1. So the angle theta will be 3 pi over 4, huh? So theta equals to 3 pi over 4, not negative pi over 4. Yeah. Okay. So I basically compute this tangent inverse of -1, right? When I compute tangent inverse of -1, if you use calculator, you will get -pi/4. Okay, but -1, 1 is not in quadrant -1, it's not in quadrant 4, it's in quadrant 2. Okay, that's why I use this notation here, equivalent. Okay, just to help us get a feeling of where it is located, but then you adjust the theta. Now, how about the phi? The phi will be cosine inverse of the z, which is square root of 6, divided by the rho, which is 2 radical 2. That is cosine inverse of radical 3 over 2. That is pi/6.
Professor.
Yes.
On the previous, when you got the theta for the inverse of tan, and you got the -pi/4, where did you plug that -pi/4 into to see which quadrant it was in?
Oh, -pi/4 is in quadrant -1. So here, basically here. Here. This is -pi/4.
Okay.
Right? But then when we see the coordinate -1, 1, it's supposed to be located in quadrant 2. So what we do, actually, we adjust -pi/4, you add pi, because the period for tangent is pi, right?
Yeah.
So when I add pi, then I will get an angle in quadrant 2.
Okay. Thank you.
Okay. That's for number 22. Now let's see number, which one is good? I think I will do number 24. Number 24, we have square root of 6, pi/4, and square root of 2 in cylindrical, and I want to find the coordinate in spherical. Okay, well then the theta must be the same, huh? Right? The theta equals to pi/4, so I just plug that in right away. How about the rho? Take a look on this picture here. This is the z, this is the r, this is the rho. This is the phi. Okay, so if I want to find the rho, I basically need the r and the z. Is it right? Okay, that is square root of 6 squared plus square root of 2 squared. That's square root of 8, which is 2 radical 2. Now, how about the phi? The phi is cosine inverse of z over rho. The c is square root of 6. The rho is 2 radical 2, which is cosine inverse of radical 3 over 2. That's pi/6. Okay, finally number 26. Let me do it here. No, not number 26. Number 30, I meant. Number 30. We have 4 pi/4 and pi/3 in spherical. What will that be in cylindrical? Oh, the theta must be the same. The theta equals to pi/4. Okay. The c will be rho cosine phi. Is it right? That's 4 cosine pi/3. That's 4 times 1/2. That's 2. The C is 2. Why I put it there? The C is 2. The 2 is here. And the R is rho sine phi. That's 4 sine pi over 3. That's 4 times radical 3 over 2. That's 2 radical 3. So this is 2 radical 3. Okay, now I remember that you have this type of question in your quiz, right? The one that you need to turn in on Wednesday. Please make sure that you show the work the way I show it too. Okay, now from here, then I want to go on with some important equation or important shapes regarding the spherical coordinate system. The first one, of course, when rho equals to constant. Let's say, for example, if rho equals to 2. Well, rho equals to 2 means rho squared equals to 4. But rho is x squared plus square root of x squared plus y squared plus c squared. Okay, this gives us a sphere with radius that constant. In this case, in this example, this is a sphere centered at origin with radius 2. Okay. How about if we have theta equals to constant? Well, theta equals to constant, it's the same to what we have in polar coordinate system and cylindrical coordinate system. So I will not discuss. Should we discuss that a little bit? Yeah, let's say, for example, theta equals to 2 pi over 3. Then you apply tangent theta equals to tangent of 2 pi over 3. Y over x equals to negative radical 3. So y equals to negative square root of 3x. But remember, this is in 3 dimension, right? So in 2 dimension, it is actually a line through the origin. It looks like this, right? But in 3 dimension, then it becomes a plane. Okay, let me try to graph that. Yeah, it becomes a plane that maybe something looks like, sorry, something looks like this, in which the angle here is 2 pi over 3. Okay. Why I use this color? Sorry. Okay, so that's what the plane look like. Okay, and then the third one, I think this is the most interesting one. Phi equals to constant. For example, when we have phi equals to, let's say, pi over 6, then notice that cosine phi equals to cosine pi over 6, but cosine is z over rho, right? And this guy on the right hand side will be I'm sorry, not z over rho. Yeah, z over rho, that's right. And the right hand side is what is cosine 5 over 6? Radical 3 over 2. If I square both sides, I get c squared over rho squared equals to 3/4. Okay, now take a look what actually happened. Take a look what actually happened. This becomes 4c squared equals to 3 times x squared plus y squared plus c squared. Cleaning up, I get basically c squared equals to x squared plus y squared. That is actually a cone. To be more precise, bicone, 2 cones. Okay, pictorially, we see it. No, it's actually not bicone. I'm sorry. No, it's not bicone. It's only a cone, not bicone. That's a very wrong statement. So in 2 dimension, okay, but this is z-axis. This is the r here. Okay, your angle from positive z-axis is 30 degrees, right? Approximately something looks like this. Now notice that we are missing the theta there, right? In other words, if I rotate that with respect to z-axis, I actually get a cone. Okay, we actually have a cone. If we convert that into polar or into cylindrical, it's actually better. So notice that if I use phi equals to pi over 6, and then I'm sorry, this should be 3x squared here and 3y squared here. Okay, and then I apply is it tangent? Yeah, apply tangent phi equals to tangent pi over 6. This will be 1 over radical 3, but the tangent of phi is r over z. Okay, if I square both sides and cross multiply, I will get 3r squared equals to c squared, which gives us 3x squared plus y squared equals to c squared. Okay. Now we will see more this kind of equation in future, but let me see if there are more equations that is interesting to play with. Let's say if I take let's say, hold on. Let's say I pick number 46 from our handout. Can we identify what is the shape of this graph here? This is rho squared sine squared phi minus 4 rho squared cosine squared phi equals to 1. But rho squared sine phi equals to r, so this is r squared minus 4c squared equals to 1, right? Into polar. In rectangular, this will be x squared plus y squared minus 4c squared equals to 1. But from here, if we try to sketch that, if this is c and this is r, it will be something looks like this. Okay, but then we rotate with respect to z-axis, so it is actually hyperboloid of one sheet parallel to to z axis. I think instead of just simply say parallel to z axis, maybe we say with z axis right away. Okay, because the following, imagine if I have the c axis actually somewhere else. Let's say the c axis is actually here, right? It is still parallel to z axis, but the axis of this hyperboloid is not z axis. The axis simply parallel to z axis. Okay, but I think if I have this, I better say one sheet with axis at z-axis like that. Okay, let me see if there are more questions that we can try to do. Maybe number 56. Number 56, I have z equals to x squared minus y squared. Suppose this is rectangular, right? Suppose I want to rewrite that into cylindrical. Well, remember, cylindrical basically change the xy into polar, and we keep the z, right? So this will be z equals to r cosine theta being squared, that's for the x squared, minus r sine theta squared. So this is equals to c equals to r squared, and then I factor the r squared out. Oh, notice that the guy inside the parentheses can be rewritten as cosine 2 theta, right? Okay. How about spherical? If we write that in spherical, this will be basically I continue from here, but I change the r into rho sine phi being squared, right? So c equals to rho squared sine squared phi cosine 2 theta. Now be very careful when you write your phi and theta. They should look very different. Okay. In fact, if you think about it, phi has the line like this, and theta has the line in the middle, like this, horizontal. Okay. Now suggested homework from here. Suggested homework from here, 12.7. Remember, this is from your handout. Please try to do number 3 to 55. Okay, just do the odd ones. Okay, that's for the end of 12.7. Let's go on to 13.2. 13.2, section 13.2 is derivatives and integral of factor functions. Okay, let's start with definition. Let our factor function Rt be function ft, gt, ht, or maybe, yeah, I would just leave it like that, where f, g, h be a function of t and element of C1. Now, this is not C prime, this is C1. If you wonder what this notation is, C1 basically means the functions, continuous function once differentiable. Okay, the first derivative of these functions are continuous. Later on, if you see C2, it means the first and the second derivative are continuous. Okay, so this is not C prime. This is not C prime. This is C1. You will see C2, C3, and on. I think in this class, the most you will go actually C2. Now, suppose we have those, then R prime T is equal to derivative of that factor functions is actually the factor of the derivatives of each functions which are components of that factor. In other words, we do the derivative component by component, but rewrite that in a factor notation. Okay, and the integral of factor function of t respect to t is equal to the factor integral, the factor which is integral for each component. Now, when you write your integral sign, please don't make it too small. Okay, I saw in the past a lot of students, when they write their integral sign, they write it super small. They just write it like this. You know, no, integral sign supposed to be larger. Okay, supposed to be larger, and it's okay to make it a lot larger than, like, instead of like your integral sign and your F letter looks pretty much the same size. No. Okay, I have seen people misunderstood their own integral sign as an F or as an S. Okay, and for me that's silly, because that person wrote it himself and then that person misinterpreted himself. Okay, now if we have integral from a to b, basically we have a determinate integral of a factor function, then it will be integral from a to b of that ft dt, integral from a to b of gt dt, integral from a to b of ht dt, which, if the r, capital RT, be the integral, if we call this our RT here, if we call this our RT, then this will be RT from A to B, like that. Okay, those are about the notation. Those are just the notation. Let's do a simple example to clarify, to make sure that we are talking on the same page. Suppose we have RT equals to 3 cosine t, 2 sine t, and 2t. Then what is r prime t? That will be negative 3 sine t, 2 cosine t, and then 2. Okay, now the integral of RT will be 3 sine t plus constant, negative 2 cosine t plus constant. Notice I use C1, C2, C3. Okay, t squared plus constant to differentiate the constants in the x or the y or the c component, which of course we can simply write it separately as follows. Plus factor, constant factor c. Okay, Now then, how about the definite integral from 0 to pi over 2 of RT dt? Then that will be basically 3 sine t negative 2 cosine t squared from 0 to pi over 2. This will be 3 0 pi squared over 4 minus 0 negative 2 0, which will give us 3 2 pi squared over 4. Now, I assume you are reasonably good with your integrations. Like for basic integrals, standard integrals that you see in your calculus 1 and calculus 2, you should be fluent with those. Okay, no one can come to me and say, Thomas, you never teach how to do this integral, the single variable integral. No, it's not my job. Okay, it's your Calc 2 instructor's job. Of course, if you have questions, feel free to ask me. Okay, especially utilize my office hour. Okay, utilize my office hour. But at the same time, during my lecture, if you want to interrupt me, go ahead. Okay, it's better for you to ask me question before the test instead of like complaining after the test. The thing is, recently I have that too many students. They just don't. They know how to complain better, more than how to ask proper questions. You know. Okay. Now I say this for you though, because like 10 years from now, 15 years from now, I'm still here. I'm still doing the same thing. Okay. But what happened to you? Right? Okay. After this class, are you a better student? Are you ready for your good school, your dream school? Okay, what you don't want to happen is you end up going to a very good school, but you don't graduate from there. That's very sad. Okay, derivatives. We are basically done with the key component of derivative integrals of factor functions. Now we are getting into a difficult part where we want to see the interpretation and the use of derivative of factor function. Now, suppose I have a factor function in 3 dimensions. No, this is not what I want to use. Let me use this one. Suppose I have factor function in 3 dimensions. So let's say it looks like this. No, too low. Make it higher. Let's say this is my RT. And we want to observe at this point here. Want to observe at that point. So this is so maybe I need to correct something. This is the curve. Okay, managed by RT. Now if we choose some t, it's here. Okay, now what is R prime t? How do we interpret R prime t? R prime t is the factor tangent to the curve at that point. That's not what I want. That's not what I want. Okay, so this is R prime t. Okay, so R prime t is the factor tangent to the curve at RT. Okay, notice that this RT can be seen as a position factor. Okay. Now, we go further. Definition. Capital T at time t. Capital T at time t is called unit tangent factor. That's the factor tangent at that curve at RT, but the length is unique. Okay, so we can see this as R prime T, the length, the derivative, the R prime T divided by its own length. Okay, by its definition, of course, the length of unit tangent factor is 1. Okay, now notice that because this unit tangent factor is tangent factor but in unit length, now of course consequently unit tangent factor must be parallel to R prime T, right? Notice that this unit tangent factor is basically R prime T divided by some constant. Okay, so it must be parallel to the original factor, right? Okay, pictorially, we can see that this unit tangent factor is parallel to RT, but the length is only 1. Okay, I hope my graph actually explained that. This is unit tangent factor T. Okay, how important that unit tangent factor T, we will see that later. Now, for now, let's do one simple example. For example, find the equation of the line tangent to the curve C managed by our functions earlier, managed by 3 cosine t, 2 sine t, 2t at t equals to pi over 2. The way we do it, we find R prime t, which we did in earlier example, right? This is negative 3 sine t, 2 cosine t, and 2, right? So at pi over 2, we will get negative 3, 0, 2. Okay, notice that this R prime T is parallel to, is the direction factor. It's parallel to the direction factor, or we can call this the direction factor. Direction factor. if you think this way, suppose you drive on the curve, driving on the curve, right? If you drive on the curve, now this direction factor, the R prime, basically the direction of your headlight. The direction of your headlight. Okay, if you turn on your headlight when you drive a car, right? So the R prime T is basically the direction of your headlight. Okay, now, but to find equation of a line, we of course need to find the coordinate on that line, right? So we need to find what is R pi over 2. Okay, that's the coordinate at which the line tangent to the curve. Okay, so I plug that pi over 2, so this will be 0, this is 2, this is pi. Okay, notice that this is the coordinate where the line tangent to the curve C. Okay, so it is on curve C, it is also on the tangent line. Therefore, equation of the line is given by, let's not using RT anymore because we used that already, call that R 1T, just to differentiate from RT. Okay, that's equals to 0 to pi plus S times -302. So again, I use different parameter. I don't use T anymore. I use S just to differentiate the parameter I use from the parameter I use in the curve. Okay, so I get this is -3S and then 2 and then 2S plus pi. I hope I don't make miscomputation. Okay. Now next, properties of derivatives in relation to vector function. Now you can see these properties on your textbook, but I prefer to write it here, to copy that here so that I hope you can write that down also and memorize. Okay, the derivative of u plus v equals to u prime plus v prime. I think I need to clarify. Let factor u be a factor function of t, and then factor v be a factor function of t. Okay, so the derivative of the sum is the sum of derivatives. Now we learned that before, right? So nothing really new. Now, and constant multiple of a factor function, if we take the derivative, is constant multiple of the derivative of that factor function. Okay, derivative of constant multiple equals to constant multiple of the derivative. In fact, if we have functional multiple of a factor function, if we take the derivative, that is equals to, we do product rule here, f prime u plus f u prime. Okay, that's product rule. That's a scalar product of a function and a factor. When you do derivative, we apply product rule. Okay, in fact, if we go further, the derivative of dot product equals to, we apply product rule too, but in dot product version. Likewise, if we have cross product, the derivative of cross product equals to cross product rule. So u prime cross phi plus u cross phi prime. Okay, and finally the chain rule. The derivative of u as a function of ft, when we take the derivative, that is the derivative of u of ft times f prime t. Okay, basically that's the chain rule. Okay, we are basically done with this part here, but let me do some more problems with integrals. Yeah, some more problems with integrals of vector function. Okay, I think that's the part that may be on the hard side, for a lot of you. But please practice, remind yourself of those things. Okay, let me try, for example, number 36. Okay, this is basically, if I rewrite that using vector notation, this is integral from 0 to 1 of 4 over 1 plus t squared plus, I'm sorry, comma, 0, comma, that comma 2t over 1 plus t squared dt. Okay, the integral will be, let's see, the x component is easy, the y component. What is the integral from 0 to 1 of 4 over 1 plus t squared dt? I hope you memorize this. This is 4 tangent inverse t. From 0 to 1, so that's 4 tangent inverse 1 minus tangent inverse 0, which is 0. Now tangent inverse 1 is pi over 4 times 4, that's pi. The c component, integral from 0 to 1 of 2t over 1 plus t squared dt. If I use u equals to 1 plus t squared, then du is 2t dt. And u0 is 1, u1 is 2. Okay, therefore my integral now becomes from 1 to 2, not from 0 to 1 anymore. Okay, and this guy here is my du, right? That's du over u. So that is natural log of absolute of u from 1 to 2. That's natural log of 2 minus natural log of 1. That's simply natural log of 2. So the integral is, so the integral from 0 to 1 of 0, 4 over 1 plus t squared 2t over 1 plus t squared dt is 0. Integral 0 is just 0, right? To be more precise, integral 0 is 1, but because it is definite integral, I'm sorry, I said it wrong. Integral 0 is constant. Yeah, but because it's definite integral, the constant cancels, become 0. And then the y component is pi. The c component is natural log of 2. Okay, we see one more. Let me do number 40 here. My purpose is not only just go like show you how to integrate a vector function, but mainly to review your integration. Okay, this is the integral of t e to the 2t, t over 1 minus t, 1 over square root of 1 minus t squared dt, and this is indefinite integral. So the x component what is the integral of t e to the 2t dt? We do integration by parts, right? And I wonder if you remember how to do integration by parts by table. If your Calculus 2 instructor taught you. If not, you figure out. Okay? Otherwise, you just do it long way. So this is 1/2 e to the 2t. This is 1/4 e to the 2t. So the integral will be 1/2 t e to the 2t minus 1/4 e to the 2t. Of course, don't forget plus constant. I call that C1 for x component. The y component, integral of t over 1 minus t dt. How do we do this? I think I need to do substitution, huh? So let u equals to 1 minus t, therefore t is 1 minus u, and dt equals to negative du, right? Maybe I write it backward. So du equals to negative dt. Okay, so that integral then becomes integral of the t is 1 minus u, 1 minus t becomes u, and this is negative du. That's integral u minus 1 over u du. That's integral of 1 minus 1 over u du. Let me do it down here. Yeah, so that the right hand side I prepare that for the z component. This is u minus natural log of absolute of u plus constant 2. The z component, integral of dt over square root of 1 minus t squared. I hope you remember this is sine inverse of t plus constant 3. So the integral gives us 1/2 t e to the 2t minus 1/4 e to the 2t I'm sorry, I need to go back to t, huh? This is 1 minus t minus natural log of 1 minus t absolute of 1 plus c2. So this is 1 minus t minus natural log of 1 minus t, comma, sine inverse t plus constant factor c. Okay, I think I have a pretty good time before I move on to the next section. So let me do more problems when it comes to proofing. And there are some questions here I think are actually quite nice to prove, at least to practice our properties. For example, I pick questions on number 51. Okay, this is more about proving. Now, the thing is, like, I don't really ask proofing questions in your tests, maybe in your quiz, like your homework, right? But I still need to show you how to do proofing in case you go to physics or math or electrical engineering, where proofing actually comes out a lot. Okay, let's see. A proof. What is the derivative or respect to t of r t cross r prime t? In other words, what is the derivative of r t cross r prime t, but I use prime notation. Okay, now according to product rule, by product rule of cross product, this is r prime t cross r prime t plus r t cross R prime being prime, double prime T. Okay, now the thing is, of course, R prime must be parallel to itself, therefore the cross product must be factor 0. Okay, so we get R T cross R double prime T. That's the end of the proof. Okay, and then maybe one more, number 52. Find the expression for the derivative of triple scalar product of vector functions. So basically the question is, what is the derivative of u dot phi cross w? Now, if we see this as the dot product of this guy and this guy, then I apply that dot product into u prime t dot phi t cross wt plus ut dot phi t cross wt prime. Right? Now, the first term is already okay, so I will just copy paste that thing. But then for the second part here, I need to do the derivative of cross product. So that is ut dot phi prime t cross wt plus phi t cross w prime t. Now, of course, I need to distribute the dot product, right? So this is u prime t dot phi cross w plus u dot phi prime cross w plus u dot phi cross w prime t. Now, I actually have a reason why I went over this. Going back to your calculus 1 though, we know that fg prime in calc 1, the derivative of the product of two functions, is the sum of g prime g, f prime g plus fg prime. Right? Have you think about what happened if we have the product of three functions and you do the derivative? You will see it actually looks like this. It will be f prime gh plus fg prime h plus fg h prime. It's like it becomes three terms, but then the primes being applied to each function one by one. Okay? Now, if we mimic that here, this is the first derivative of the first function, the first derivative of the second function, and the first derivative of the third function. Okay, but it maintains the same pattern of dot cross, dot cross, dot cross, dot cross, dot cross. And of course, you need to keep the order also, because when it comes to cross product, the order is important. Okay. We don't have commutative property in cross product. We still have commutative property in dot product, but not for cross product. Okay? Suggested homework from this section will be suggested homework from section 13.2 will be from 9 to 25 and then 35 to 41. Okay, now right now it's 5:41. Let's take a break. We come back at 5:51. The next section we will go over is 13.3. I don't think I can finish this section. It's a bit longer than 1 hour sections. And I'm not rushing to finish it. Let's take a look. Section 13.3 on arc length. First one, arc length. And then the second part is on curvature. I will add one more arc length and parameterization, I want to say, and parameterization. And then, am I recording this? Yeah. And then curvature, but then I want to also emphasize one important ingredient of this section that our textbook seems not to emphasize. I don't want to overemphasize that too, but at least I want to mention that that's a Frenet frame. Frenet frame. Or TNB frame. Okay, I believe I can finish part A very well, and then I can go over a bit of the parameterization, and then I think from there I will go to curvature. Now the TNB frame, I may leave it till the next meeting. Okay, now TNB frame is being used a lot in physics, especially if you are going to aerospace engineering, okay, or like going to NASA, JPL, anything with missile, anything moving in space. Okay, let's start with arc length from our Calc 2, arc length and curvature. I'm sorry, reparameterization. Recall that in Calc 2, if we have a curve, like xt, yt, or we have a curve y equals to ft, then the arc length from, I'm sorry, no, not ft, fx, then the arc length from t equals to a to t equals to b, the arc length denoted by a cursive capital L from A to B is given by integral from t equals to a to b of square root of dx dt squared plus dy dt squared dt. Okay. Basically, this is what actually happened. So like, suppose if we super enlarge that curve, right? Super enlarge that curve, and we break this curve here into a lot of small segments, and we approximate the length of this curve, we basically add the length of these segments, line segment. Okay. If we take one of the line segment, let's say this guy here, and we super enlarge that, you will see the length here, usually denoted by ds, is basically application of Pythagorean theorem on dx dt, dx dy. Okay. And what we will do is the arc length is basically the integral from a to b of those ds. So you have ds here, the length of that segment, the length of that segment, the length of that segment, and then you add all of them. Okay, we get the arc length. Now, then, that ds, however, is the Pythagorean application of dx squared plus dy squared. Okay, now from here, then, we have some different ways of expanding it. If we have x and y are parameterized by dt, then by t, then dx is equals to basically dx dt, right? Maybe that's yeah, dx, the derivative of that, right? Okay, and then we have dy dt. Those are the derivative, right? Times dt, dx equals to dx dt times dt, and then the dy is dy dt times dt. In other words, notice what happened to that integral now from a to b, or square root of dx dt squared dt squared plus dy dt squared dt squared, which I will factor the dt out under square root, and we get dx dt squared plus dy dt squared, and we factor out dt. Okay, or if our y happen to be a function of x, then dy equals to dy dx times dx, right? And if I substitute that integral, I get integral from t equals to a to t equals to b square root of dx squared plus dy dx squared dx squared, which I will factor the dx squared under square root out. Okay, that would be 1 plus dy dx squared dx. And if you remember, we actually have another formulas for arc length in 2 dimension if x is a function of y, right? Okay, the one we will use actually just the first one when it is parameterized. At that time, actually using what we know right now, suppose our curve is managed by RT in 2 dimension, which is xt and yt. Then we can use this notation now from A to B of the length of R prime t, right? Because R prime t is the factor function x prime t, y prime t, and the length of that R prime t is square root of x prime squared plus y prime squared as a function of t. Okay, that's in 2 dimension. Now, in 3 dimension, in 3D, the ds, the length now is in 3 dimension. Right? Suppose I have a curve in 3 dimension. Okay, notice that it is in 3 dimension. So you need to imagine that instead of only dx and dy, we actually have dx, dy, dz. Okay, do you see that? Okay, so this is our dx, this is our dy, and this is our dz. Okay, so in other words, suppose our RT is managed, our curve is managed by factor function RT, which is xt, yt, zt, parameterized by t, right? Then our R prime t is x prime t, y prime t, z prime t, whose length is square root of x prime squared plus y prime squared plus z prime squared. Okay, and our arc length from time A to time B equals to still integral from A to B of the magnitude of that R prime t dt. So notice that even though one of them is 2 dimension and the other one is 3 dimension, but if we use RT parameterization, that will be basically the same formula, but in details, of course, one of them 2 dimension, the other one 3 dimension. Okay. In other words, maybe let me write it here. And the arc length from A to B of curve C is integral from A to B of square root of x prime t squared plus y prime t squared plus c prime t squared. Hold on. Point is dt in 3 dimension. Okay, I prefer to memorize this one because this is basically applicable to a two-dimension or three-dimension. Okay. Now let's go on further. Something called displacement definition. Displacement function. Or maybe distance function to be more precise. If the formula we have earlier we have this integral from a to b of magnitude of r prime t dt. That's the arc length from a to b of curve managed by rt, right? Okay, this tells us the arc length of C managed by RT between, maybe in the interval AB. Okay, now, so if I have a curve, let's say I have a curve, this is curve C, and this is when t equals to 0, this is when t equals to A, this is t equals to B. This formula earlier here managed the length from this point to this point. Of course, the output will be a number. Okay, the output will be a number. That's distance. Now, displacement function or distance function actually do something else. Okay, suppose we are interested. Suppose we want to know the distance traveled, the distance or displacement traveled along curve C from t equals to 0 as a function of time t. Then we call that ST. To be more precise, SAT if we come from time A. So let's say you start from time A, okay? But then instead of fixing our end time to be t equals to b, we don't fix it. We call that t in general. Then it will be integral from a to t of magnitude of r prime s d. Yes, you know what? Let me don't use s. Yeah, I use s then. I need to use different variable though. I need to use different variable, different from the t. Let me think of something else. Maybe u, because we already have s there too. Okay, let me use u. So notice that this will give us the distance. This will give us distance function. Notice that it is a function. Distance function traveled along from t equals to a as a function of t. Okay, so kind of like imagine this. Suppose I like to go to Vegas, by the way, And let's say this is Fourier 10 and this is Fourier 10, let's around West LA College. So the exit of Overland, right? Okay, and then this is Fourier 10, and then we have Fourier 15 here. And suppose there's no traffic, okay? Suppose there's no traffic. Now then the distance from West LA College to the junction Fourier 10 and Fourier 15 is approximately 1.5 hours. And from this junction here to Las Vegas is approximately 3 hours. Let's say 3 hours. So a total of, let's say 2.5 hours. So a total of 4 hours from West LA College going to Las Vegas, right? Okay. Now, the question is basically as follows. Okay. Suppose somebody asks you, how far you have traveled. Oh, I have traveled for 1.5 hours. Okay, then can that person tell approximately how far you have traveled along this path, right? Okay, oh, this person already traveled because Fourier 10, it's a straight without traffic, maybe some traffic, then it will, from this West LA College to this point, you must have traveled approximately 55 miles. Okay, like once you tell me the time, I can tell you how far you travel. Okay, notice that RT is position functions, right? That's position function. So if you tell me the time, then I will tell you the position, right? How long have you traveled, Thomas? I traveled 1.5 hours. Oh, okay, then you must be around the intersection between Fourier 10 and Fourier 15. Okay, now this function here tells us the distance you have traveled along a specified curve. Okay, now let's do some example to see those better. For example, let's say RT equals to e to the 2t cosine 2t, e to the 2t sine 2t, and 2. Now R prime t will be, you become very busy, huh, with this, huh? Okay, 2e to the 2t cosine 2t minus 2e to the 2t sine 2t, 2e to the 2t sine 2t plus 2e to the 2t cosine 2t, comma 0. The magnitude is, oh, you know what, before I really compute that, let me factor the 2e to the 2t, 2e to the 2t cosine 2t minus sine 2t sine 2t plus cosine 2t, comma 0. So when I try to compute the magnitude, you see we have common factor, right? Okay, then it will be the absolute of 2e to the 2t. The nice thing is 2e to the 2t is always positive anyway, but I need you to be aware that it's supposed to be always positive because it is in sense of a line, I mean the length, right? Okay, and then I do the square root of whatever inside the factor notation. So cosine 2t minus sine 2t squared plus sine 2t plus cosine 2t squared plus 0 squared. This is 2e to the 2t square root of cosine squared 2t minus 2 cosine 2t sine 2t plus sine squared 2t. Go on. That's sine squared 2t plus 2 sine 2t cosine 2t plus cosine squared 2t. Notice that this guy cancels with this, right? And this guy plus this guy is 1. This guy plus this guy also 1. Okay, so we actually simplifies to be 2. Give me a second. So this becomes 2 square root of 2e to the 2t. Okay, now suppose then the question is, how far have you traveled from time 0 to time t? How far have you, what is the length? If you travel for t units of time, how far have you traveled? Well, then it will be integral from 0 to t of 2 square root of 2 e to the 2u du. Notice that I need to use different variable for my integration and variable for my distance function. Okay, and this will give me square root of 2 e to the 2t. Okay, maybe I go slow down a little bit. Okay, so it will be 1/2 times 2 square root of 2 e to the 2u from 0 to t. Right? Oh, now I see my mistake. So the 2 cancels, I get square root of 2 e to the 2t minus e to the 0, which is 1. So this is the distance traveled after t units of time along these curves. Okay. Now, reparameterization. Curve reparameterization. This concept is a bit harder to understand. Let's try. The way we learned it earlier is we have a curve. Maybe it looks like this. Let's say this is curve C managed by RT. Basically, if you tell me the time t, let's say this is from time equals to 0, this is time equals to 1, this is time equals to 2, and because we are going to a loop or we are exiting a freeway, then we slow down, right? But the time keep on ticking, and then the street is almost straight and no traffic, then we go faster. Okay, so you see between time to time, this length here is 1 unit of time, but the length is different from here. Okay, it's still 1 unit of time, but the distances are different. Okay, now when we say we want to reparameterize the curve, we want to reparameterize it this way. In terms of length, suppose this is when s equals to 0. Now, after 1 unit of length or 1 mile, you see, we will reparameterize that into same length. You see what I mean? Okay, so earlier, using this vector function RT, you tell me the time, I tell you the position. We want to change this into RS, instead of you tell me the time, you tell me how far you are from the original point. I can tell you your position. Okay, so earlier we have pretty much this scheme here. Once you tell me the time, I tell you the position, right? Okay, which is RT. Now, with ST earlier, we get ST, this is the distance, once we know the time t. Now, this expression here is basically position function of distance traveled after time t. Okay, it's basically the same thing. Now, the question is, if we know how far you travel, can we find your position? Okay, so now we have position in terms of how far you already travel. This is position at time t. Okay, this is the position after traveling distance s. Now notice that something very important. Notice that the distance function turns out to always be a one-to-one function. Okay, once you tell me the distance, the time, I will tell you the distance. Of course, as you travel, the distance only increases, right? Okay, the distance only increases when you travel, the distance increases, and therefore the distance as a function of time must be a one-to-one function. Let me write it as a comment somewhere here. Notice that maybe I use red color. Notice the longer we travel, the further we travel. In other words, as t increases, our distance travel also increases, but that forms as t, it must be a one-to-one function. Now, because it is one-to-one function, then there must be a way, since as t is one-to-one, then Ts, I know the notation seems to be strange, is the inverse of St. If you tell me the distance traveled, I can tell you the time. Okay, why we need that? Because what we need to have is Rs, right? Okay, once you tell me the distance travel, I need to change it back to time first. I need to go back to time first and then go to the position factor function. Okay, So RS is basically, you will see later on, you bridge it, you need to find the t as a function of s first. Okay, RT equals to RT as a function of s. Suppose I use the example we have earlier here. Suppose I use this example here. Notice that S0t equals to square root of 2e to the 2t, is it right? And then minus 1. Now notice that we have factor function RT, which is e to the 2t cosine 2t, e to the 2t sine 2t, and then 2. Once you tell me the time, I can tell you the position. Now, can we find how far you have traveled? Tell me the position. And to do that, I need to find t as a function, the time as a function of distance traveled. Okay, basically I reverse this as over square root of 2 plus 1 equals to e to the 2t, apply natural log, and then divide by 2, give us the time t, right? Notice that now then we have time as a function of distance is 2, 1/2 natural log of s over square root of 2 plus 1. Once you tell me the distance you have traveled, I can tell you how long have you traveled. Now I will put this back here. The position as a function of distance traveled is e to the 2t is s over square root of 2 plus 1 cosine natural log of sine s over square root of 2 plus 1. That's for the first component. The y component, s over square root of 2 plus 1 sine of 2t, which is natural log of s over square root of 2 plus 1, comma 2. Okay, let me make it a bit smaller, or maybe, hold on. Move this a bit closer there and make it a bit smaller. Okay, so now this is the curve reparameterization. Instead of you tell me the time, I tell you if the input is the time, the output is the position. Now, if you tell me the distance you have traveled, I can tell you the position. Okay, now that is what we call surface reparameterization. Okay, now let's do more problem. Another example. Suppose we have RT equals to e to the t, e to the t sine t, and e to the t cosine t. Basically, this is e to the t, 1 sine t cosine t. And then we want to find part A, find the equation of the line tangent to C, to curve C, t equals to 0. Then we need to find first what is R0. This will tell us the position. R0 will be 1, 0, 1, right? And then R prime t will be e to the t 1 sine t cosine t. I do product rule on this guy here. I do product rule on this. Plus e to the t 0 cosine t negative sine t. Now at 1, I'm sorry, at 0, that will be 1, 0, 1 plus 0, 1, 0. That will be 1, 1, 1. That's the direction. Okay, so the equation of the line, tangent line, is given by, let's call that R1 S or R1U maybe, just to differentiate that with the T. R1U equals to the position plus U times 1, 1, 1, which is U plus 1, U plus 1. Okay, that's the line. So imagine you have a curve. At that point, you have the vector. This is R prime t. Okay, while this is the RT. Okay, next, how about the unit tangent factor? That's R prime t divided by its own length, right? So let's find out first what is R, the length of R prime t. Okay, the nice thing is we already have the e to the t, right? Imagine if I have this, but I combine the factors, okay, I will get 1 sine t plus cosine t minus sine t. So I need the length here, right? Okay, which is equals to e to the t square root of 1 squared plus sine t plus cosine t squared plus cosine t minus sine t squared. That gives us e to the t square root of 1 plus 2 sine t cosine t. That's for the second term. This is the first term, the second term, and the third term. Because cosine squared plus sine squared equals to 1, right? You are in Cal 3. I assume you are able to do that. And that gives us square root of 3 e to the t. Okay, so what is the unit tangent factor? Unit tangent factor will be that R prime t divided by its own length. Okay, that's e to the t 1 sine t plus cosine t minus sine t divided by square root of 3 e to the t, which will give us, let me still keep that 1 over square root of 3 factor. 1 sine t plus cosine t, cosine t minus sine t. Now, just in case we want to find, oh, you know what? Can you reparameterize? Reparameterize C as RS, basically C factor functions as a function of distance instead of as a function of time. Then we go back to that S, right? As 0t from t equals to 0 equals to integral from 0 to t of square root of 3 e to the u du. That will give us square root of 3 e to the t minus 1. In other words, s over square root of 3 plus 1 equals to e to the t, and t itself is natural log of that. Now I put it back to r. Rt is, if we look back, Rt is, what is that again? Let me copy paste this thing. Rt is this, right? Now, so Rs will be s over square root of 3 plus 1, that's for e to the t, times 1 comma sine of natural log of s over square root of 3 plus 1 cosine of natural log of s over square root of 3 plus 1. Once you tell me how far you have traveled, then I can tell you where you are located. Okay? Now, I will go on further to something into a new definition. Factor n t. Factor n t is the unit factor normal to C at t. What is that? Suppose I have a curve. Let's say this is the curve, C, which is managed by RT. And we have at this point here is the R prime T. Now we have learned earlier that this is our unit tangent factor with length 1. Now, normal factor, unit normal factor, the capital N there is this factor. What color should I use? Let me use dark green. Unit normal factor is here. The direction of that factor is actually in the direction where, if you imagine if you have maybe a rope like this, okay, and then you bend it to be like this, okay, then that rope, if you release that rope, then that rope will come back to the straight one. Okay, so this is the factor. This is the factor in that direction. If you go through, if you exit a freeway or you enter a freeway, usually we have some loop, right? Okay, usually we have some loop. Okay, now then you will feel that you are thrown away from that loop. And for you to be not to thrown away, then you basically need to apply a factor normal to it, a force normal to that, opposite of that. So imagine centripetal and centrifugal force, if you happen to know that from physics. Okay, or you may think this way. Suppose you have a car. So we used that illustration earlier, right? Going through this curve. Now, I said earlier that your headlight is basically your R prime T, whose unit is the capital T, okay? Now, when you go through this curve at certain speed, then this unit normal factor here, is basically the action your bodies apply so that your body is not thrown away from that curve. Okay, so imagine if you are in the car, right? If you're in the car driving, okay, and then you turn to that way. Let's say you turn right. Strangely, your body will kind of bend a little bit to the right. Why? Because if you don't make your body like that, your body tend to be thrown to the left in your car. Can you imagine that? Okay, now this unit normal factor is the factor that shows to which direction your car is actually turning, but this unit normal factor here is perpendicular to T. Okay, you will see that this unit normal factor here is perpendicular to that unit tangent factor. Now the thing is, it is normal. Okay, so you will see that the unit normal factor, the formula is basically the derivative of unit tangent factor divided by its own length. That's basically to make it a unit length. Okay. So if we go back, we already have the T there. Our unit tangent factor we have above is what? 1 over radical 3, 1 over radical 3, 1 sine t plus cosine t minus sine t. That's what we have up there, right? Now then, if I do the derivative, the good thing is the coefficient is constant, so I will just leave it like that. 0 cosine t minus sine t, and then negative sine t minus cosine t. And the length of that t prime t is 1 over radical 3 times square root of 0 squared plus cosine t minus sine t squared plus negative sine t minus cosine t being squared. That is 1 over radical 3 square root of 0 plus 1 minus 2 sine t cosine t plus 1 plus 2 sine t cosine t, which will give us 1 over square root of 3, and inside you see the sine t cosine t cancels. Yeah, square root of 2. Basically, we have square root of 2 over square root of 3. Now, then what is the unit normal factor? The unit normal factor will be the t prime t 0 cosine t minus sine t, and then negative sine t minus cosine t divided by square root of 2 over square root of 3, which is equal to 1 over radical 2. So notice that the unit normal factor for sure is, this is just a remark, this must be parallel to t prime t, but the length is 1, right? Okay, that's why notice that we basically maintain this part here, but we make that length to be 1. Okay, we make that length to be 1. So the length of this factor here is radical 2. To make it unit, we divide by the length, which is square root of 2. Okay, now one more, last one. Let me use back to my regular color, B, T, capital B, T. That's binormal factor function. Is defined as the cross product of T cross N. Okay, so suppose I try to graph this in 3 dimensions. I hope it's possible. Suppose I have a curve that is actually coming this way. Okay, let's say this is my RT. Now, at this point here, let's say this is my unit tangent vector. Okay, and my unit normal factor is like this, which is on this. Okay, I wonder if you can imagine on this plane here, right? Okay. Now then the B the binormal factor will be perpendicular to that. Oh, what happened? That's the binormal factor. Okay, now the one I need to explain is the following. Let me find a picture. The time is almost up. I have less than 5 minutes, but let me give you some picture here. I hope I can find a way. Maybe I use this one. Okay, let me use this one. Now, notice that this red curve here is actually moving in this direction. This red curve. And notice that the t, the factor t, is always tangent to the curve as your headlight, right? Okay. Now, unit normal factor, however, is always pointing to where the curve concave to. So like this one at this point here, the curve is actually concave this way, right? Concave open to that side. At this point here, it's actually open to this side. And at this point here, it's maybe just a little bit, right? But because it's unit, then the length still the same. Okay. Now, because this is my t, t cross n like this, then the b here seems to be shorter, but it's because it's going into the table. Okay, going into the paper or going into the picture. Okay. While this one here, suppose this is the t going to this direction and n going to that direction, then the b is supposed to again go into the table, go into the paper. Okay. Remember the right hand rule, right? Okay, so this is t, this is n, then it will go into the paper. Okay, now that is TNB frame. Now the thing is, let me delete this. We have some planes that we need to be aware of. Suppose I have a curve. Maybe I redo it again. And let's say this is my curve. Okay, and I want to observe the TNB frame right at that origin here. And you will see that the unit normal factor is actually pointing, unit tangent factor. Unit tangent factor at that point is actually pointing this way. Okay, and then the unit normal factor is pointing this way. Now the binormal, what color should I use? let me use orange. The binormal will be T cross N. Okay. Now, some definition. Rectifying plane is normal to normal factor. So rectifying plane refers to this plane here. The plane that is spanned by T and B. Now, N is the factor normal to that rectifying plane. Where are we going? Why we need to learn this? It has something to do with planes. Suppose this is our plane here. Okay, we see the plane from above. Okay, then the rectifying plane is this. This is the rectifying plane. Okay, the plane turn left or turn right, actually, by modifying the rectifying plane, which is usually at this position here, at the, like if you see the plane from sides, right? Okay, the rectifying plane, then the plane may be able to turn left or right a little bit by playing with this fin here, this part. Okay, that's rectifying plane. Now, osculating plane is the factor normal to binormal factor. So that plane is basically this plane here, the one that is spanned by T and N. Now we can imagine the normal plane, osculating plane of an airplane basically being controlled by, so if you have an airplane, right, it is being controlled by the wings. Okay, so this is the osculating plane. The rectifying plane is this one. Okay, so rectifying planes helps the plane turn left or right. Osculating plane helps the plane go up or down. Okay, of course, passenger plane actually cannot go down. You go cannot face down. Passenger plane cannot turn from horizontal and then becomes like this. No, you cannot. Okay, the plane can land, but the way the plane land is by slowing down. Okay, but the plane is still facing up. Okay. Now, what is normal plane? There's one more. Normal plane is the plane normal to tangent plane. Normal plane is perpendicular to tangent factor. Okay, so tangent plane, normal plane is basically the plane that is spanned by N and B. Okay, now if the air drag of an airplane. If you see the airplane from the front, right? The air drag of an airplane has a lot to do with the area of its normal plane. If you see that from above, that's why if it is doing some braking in the air, it's basically increasing its normal plane. Okay, the area of the normal plane. By increasing the area of the normal plane, then it has a much larger air drag and therefore will slow down the plane. That's why if you look at the fighter jet, for example, the way they design the fighter jet, the sideways may be skinny, right? Okay. They try to make it in a way that the cross section, the normal cross section, is as small as possible. The area is as small as possible, such that it can accelerate and the air drag will be minimized. Okay. Now, I have not covered the notion of curvature in this section here. Okay, but I can already give you the suggested homework. Let me give you the suggested homework from this 13.3. Let me call that part A. From number 1 to number 6 and 17 to 20, just do part A. Okay, now then on Wednesday, when we come back, we will work on curvature 13.3 and then go on with 13.4. Okay, that's for today.